Okay, I hope I said share screen.
Okay, is that for both lectures or just the first one?
That's for both.
Okay.
Yeah, I might tinker with them a bit for the second lecture, but not very much.
Right. So in a few seconds, I'm going to mute everybody, and then Sebastian and Simon Donaldson should unmute themselves, and then you can start. Okay?
Yes, sir.
Sebastian?
So, yeah. Hi, everybody. It's my pleasure to introduce Simon Donaldson now from Imperial College in Stony Brook, who's going to talk about deformations of singular sets. You can see it on the screen, actually, and that's part 1 today. So.
Oh, thank you to the organizers for inviting me to give this talk, or these 2 talks, in fact. Yeah, hang on. So this is the plan for the 2 talks. The first part, I will describe the problems that I'm interested in. So these problems will be this will be quite somewhat different from the rest of the talks in this meeting. In fact, quite different. But I will explain that there are at least some maybe slightly tenuous connections between what I'll be talking about and other things that have been discussed this week. And so I will do that in the second part. Then later, this will probably be more like tomorrow, I'll talk about more about some aspects of the proofs. And then I'll have another section, if time allows, explaining more context and where the ideas I'll be discussing fit in, at least perhaps in some cases conjecturally, with various other developments. So let me begin. It'll take a bit of time to, I hope, explain reasonably clearly exactly what we want to discuss. Now, there are 2 problems. Actually, the central one will be the second one, but the first one is slightly simpler and gives some orientation. So for the first one, we're considering a Riemannian manifold, n-dimensional manifold, and a fixed codimension 2 submanifold. Everything has orientations, and we suppose the class of this submanifold in homology is even, which means 2 things. One is most familiar. We can take a double branched cover, m tilde, mapping 2 to 1 down to m with branching over sigma. We can also construct a flat real line bundle with V over the complement of sigma, which has got non-trivial holonomy on little loop locally linking sigma. Sigma has got codimension 2, so we take a point in sigma, you can consider a little loop running around in the normal space. So perhaps the clearest way to introduce the things we're interested in is to say that they're harmonic 1 forms on the complement of sigma in M with values in this flat bundle. So to say there's sections of the cotangent bundle tensored with this bundle, the flat bundle. Because the bundle is flat, we know what D and D star are acting on these sections, and we want the form to be closed and closed. So lifting up to the branched cover, of course, this trivializes when we lift the bundle, it becomes trivial. So these become ordinary 1 forms when we lift them up to the branched cover. But of course, we can lift the Riemannian metric on the complement of sigma to the branched gamma, and these things will be harmonic one forms up there. But this metric will be singular if we want to view it as a Riemannian metric on M tilde. But one can, it's not hard to show that if A is, so A is initially defined just on the complement, if it has some sort of reasonable behavior, say requires to be an L2, then one can show that this lifted form still defines a de Rham cohomology class on M tilde. And in fact, by construction, it will be in the negative eigenspace for the action of the involution that we have on M tilde acting on the H1 with real coefficients. Conversely, if we take such a class in this negative eigenspace, then one can show that it comes from some A. If you like, this is a version of the Hodge theorem on M tilde applied to this singular Riemannian metric. That would be a way of thinking about it. So we're interested in the question, when does this form, this twisted harmonic one form, when is it actually bounded on the complement? So to get some sense of what this means, why it might be interesting, let's consider the fundamental example, which is when our dimension n is 0, so sigma is just a finite set of points in a surface. But this harmonic condition is actually conformally invariant in 2 dimensions. So we can just think of M as a Riemann surface, as we like. We don't, rather than a Riemannian manifold. And then we have a complex geometry translation of what we're doing. We can write A as the real part of a holomorphic one form on the complement with values in this, this bundle. But if we take the square, then when we square V, it becomes trivial. So this is an ordinary holomorphic quadratic differential on the complement of sigma in M. So how does this look in local coordinates? If we take a coordinate centered on a point of sigma, coordinate Z, then saying that A is in L2 means that we can write our one form in this form. So of course, these are multi-valued functions, these fractional Z to the minus a half, Z to the half, Z to the 3 over 2, but that's just what's allowed when we're talking about sections of this non-trivial flat bundle, essentially. So our condition that requiring our form is in L2 means that we're not allowed anything worse than Z to the minus a half. If we tried Z to the minus 3 over 2, that would not lie in L2. So we're not allowed that. So this is the general alpha that we're considering. And then correspondingly, when we take the square, we would get, in general, a term Z to the minus 1 times dz squared. So typically, we will get a meromorphic quadratic differential with a pole at this point. The condition we're interested in, which is the form is bounded, is just that this Z to the minus a half term is absent, C0 is 0. So that's just saying that our quadratic differential is actually holomorphic. So in fact, it will have a 0 at this point. The square will be given by the square of the next term. So the condition which we'll see, we'll be interested in, which is that this next term is non-vanishing is just saying that this quadratic differential has a simple zero at this point. So for our purposes, it's easier to express things not in terms of one forms, but in terms of essentially locally in terms of functions, or globally in terms of sections of bundles with one-dimensional fibers. So let's, this is quite elementary, but maybe not completely familiar, so let's just review it. If we just do something completely standard, if we have a manifold, say W, and a one-dimensional real cohomology class, then we can use that to construct a flat bundle with fiber R, but not a line bundle. The structure group of this bundle will be R under addition, so there's no preferred zero section of this bundle. But this has the property that sections of this bundle exactly correspond to the closed one forms on our manifold representing this given cohomology class. And this is if we think of taking a check representative for this cohomology class, then we know that one-dimensional cohomology classes, what did I say? Yeah, so we take a check representative, and then that we use that to construct this bundle. The check cocycle defines the transition function for this bundle. So this is actually a bit of a simplification, because it's easier to talk about functions than to talk about one forms. Locally, these sections of this bundle are given just by functions. So we can do the same kind of thing in our case. If we're given this cohomology class, chi, then we can form a bundle we'll call E over the complement of sigma in M. So we'll have fiber R, and the structure group will combine the translations that we just saw with the multiplications by plus or minus 1 that were involved in our vector bundle V. So the structure group of E will be the group of isometries of R. The maps take Y in R to plus or minus Y plus a constant. So when we've done that, our one form A can be obtained as the derivative of a harmonic section of E. And again, if we think about this in the prototype case of 2 dimensions on our Riemann surface in our local coordinates, we locally trivialize our bundle E, so we think of sections of E just as functions. This is saying we're considering a section which in general would have the form the real part of some multiple of z to the half and some multiple of z to the 3 over 2, where these multiples are just related in an obvious way to the coefficients that we saw before. If we just differentiate this function, we'll get the one form we wrote down before. So our boundedness condition that we're interested in is, again, that this leading term, the term we're calling A, should be 0. So going then to the case of general N, where we have this codimension 2 submanifold rather than just a set of points, the harmonic section H has an asymptotic development, one can prove, of the same shape as what we saw before. So if zeta is the obvious kind of generalization of the local coordinate z that we considered before, so local model section defined on a tubular neighborhood of sigma, then H has some asymptotic expansion with a leading term given by z to the 1/2 in general, with multiplied by a factor a. But now a will not just be a number, it'll be a section of a line bundle over sigma. And in fact, this, if we write n sigma as the normal bundle, thought of as a complex line bundle in the usual way, then the relevant section, the relevant line bundle for which A is a section, will be the dual of the square root of the normal bundle. Our assumptions mean that this square root is defined. That's part of the choice of the square root is built into the choice of our flat vector bundle. If you like, this is the normal bundle of the copy of sigma in the double cover. So there's a whole asymptotic. If this leading term vanishes, then the next term will be some multiple of the obvious generalization of the thing we call z to the 3/2 before. And an error term which should be order r to the 5/2, where r is the distance to our submanifold sigma. So we can take this setup, we take our manifold, we take a Riemannian metric, we take our submanifold, we take this cohomology data chi, we get this section of this bundle over sigma, which gives the leading asymptotics of our harmonic section, of the twisted harmonic function over the manifold. And if this happens to vanish, then we have a well-defined next term B.
Sorry, can I ask something?
Yes.
Does the fact that your section is harmonic imply that A has to satisfy some equation?
No.
Okay.
No, I don't think so. No. No, A and, well, as we'll say later, this is somewhat like, what we're discussing is somewhat like discussing the boundary theory for PDEs. So A is somewhat like A is somewhat like the normal derivative of on the boundary of a solution of a Dirichlet problem. So it's not determined locally at all. It doesn't satisfy any local conditions. So we're interested, for reasons that we'll say more about, in the situations when this leading term vanishes. And the result we want to discuss is the fact that this is a good condition in that it has a good deformation theory. In fact, very simple deformation theorem, assuming that the next term is non-zero, and it's nowhere zero on sigma, then if we deform our continuous data, the metric and the cohomology class chi slightly, then we can deform sigma slightly so that we again have a solution of this problem. So we again find a set of data for which this leading term vanishes. Oh, so I forgot to say right at the beginning, I think it was on my slide, but I forgot to say it, but this talk is related to at least one other talk I've given in these collaboration meetings. Particularly there's a talk in the June 2018 meeting. So it's in some ways a progress report following that talk. progress is not the most rapid, you see, from the dates. So I discussed a proof of this theorem back in 2018, and that's all written up, appears on the archive. We're going to talk about, well, we're going to talk mainly about a slightly more harder problem. The approach we're going to talk about could be applied to this, to give another proof, a slightly different proof of this theorem. And I should say there are the related results, some years earlier, of Takahashi, who mainly treated an analogous question for harmonic spinors rather than harmonic one-forms, in a context that I'll talk more about later. Anyway, the main reason for bringing this problem in, or one of the main reasons, is it gives some motivation for what we're talking about. This is a generalization to higher dimensions of the fact in 2 dimensions that the holomorphic quadratic differentials with simple zeros on a Riemann surface are locally parametrized by the cohomology classes that they define in this anti-invariant part of the one-dimensional cohomology of the branched cover. As mentioned in Ivan Smith's talk, and this is I don't know, a significant part of the story about stability conditions and so forth in that setting discussed there of involving quadratic differentials and stability conditions. So maybe it's just to see what this means. So that's to say, if we're just considering, if we vary our quadratic differential, we're allowed to vary the points. So this is precisely, moving your points is precisely what you mean to say is that you can deform to have a holomorphic quadratic differential with those zeros rather than those poles. So in a few minutes, so in part 2, we'll give some more motivation for that. But let's go on to describe the second problem, which is a more nonlinear version of the first one. The first one is also not really linear because we're studying a linear PDE away from the singular set, but this condition on the this condition A on the vanishing of A is not a linear condition. Of the deformations of sigma are not a linear object. So let's consider this sort of harder problem. We start with the standard vector space with the quadratic form of indefinite signature NM, where M will be positive in our situation. So an n-dimensional submanifold of this space is called positive if its tangent spaces are positive subspaces in the usual sense. There'll be maximal positive subspaces. You might, if M is 1, then you might want to call these space-like subspaces, thinking of Rnm as being Lorentz space. So we can do differential geometry on submanifolds in these indefinite spaces in much the same way as we do in Euclidean space. We have an induced volume form on these positive submanifolds. So we get Euler-Lagrange equations associated to the volume functional in the familiar way. Unless we can also define the mean curvature of any one of these positive submanifolds, and the equations say the mean curvature is 0. The mean curvature is a normal vector field, as usual. So in the Euclidean case, what we'd have would be minimal submanifolds. In this indefinite case, the solutions are called maximal submanifolds because they turn out to be, in a sense, local maxima of the volume functional, in a suitable sense. So let's just see what these are explicitly. Supposing we take M is 1 and consider submanifolds given by the graph of a function on Rn. So we can do that either in the Euclidean setting, so we're considering that graph as a subspace of Euclidean space Rn plus 1, and then this is the ordinary minimal submanifold equation for graphs, which is a much studied thing, and both by differential geometers and PDE people. If we do the Lorentzian version, then the positivity condition says that the norm of our derivative should be less than 1 in order to have a positive submanifold, and the equation is just the same thing with a change of sign. So these are, of course, nonlinear equations. If we want to think about them, just get an idea of what kind of equation they are. If we think of the situation where the derivative of f is small, then where the leading term is the Laplacian. So the first approximation, these are like the Laplace equation. And the next, the sort of first nonlinear term is this kind of expression. We take the product of the second derivatives and 2 of the first derivatives and take that contraction. So this is sort of gives the general nature of the nonlinearity of the PDE. For our purposes, you can more or less think of the equation as being delta f plus or minus this expression is equal to 0. Another way of thinking about this maximal condition, which relates it more to the first part, is that the maximal condition says that that is equivalent to saying that if we take the coordinate functions on the ambient space, restrict them to the submanifold, then they should be harmonic with respect to the induced metric. So in fact, if we go back, this is just if we take the vertical coordinates in this setting, this is just the Laplacian. So the vertical coordinate induces the function f by construction. This is just the Laplacian of f with respect to that induced Riemannian metric, up to maybe a factor, a scalar factor, and the same here. By, let's say, sort of by construction, whatever submanifold we took, at a given point, the harmonic functions which are in the tangential direction are automatically harmonic. So it's really just, the only condition is in the normal direction, you might say. So that's one of our main ingredients in what we want to do. To recall some more, let's just recall that if we have a vector of length, oh, sorry, this is a mistake, that should be -2 here in our indefinite space, defines a reflection by this familiar formula. If I put -1, I should have some factor in here. But, so we want to consider so these things lie in the orthogonal group of this indefinite form. We want to consider, again, affine transformations. So we have a group, gamma, which is the affine version of this orthogonal group. We allow translations as well. And we also have a set of affine reflections in this affine group, things which, with a suitable choice of origin, are the reflections in the previous sense. So now we take our manifold and codimension 2 submanifold as before, but we don't have any given Riemannian metric on M. So we begin with a flat vector bundle over the complement with fiber this indefinite space, the structure group, the orthogonal group. So the holonomy around any loop, as we considered before, is a reflection. Then we want to consider lifts of this bundle to an affine bundle, we call E, such again that the holonomy is given by an affine reflection. So without going into more details here, there's a certain cohomology group which parameterizes these lifts, just as playing exactly the same role as the H1 of the H1 minus for the double branch cover in the previous discussion. Anyway, this H1 is a finite dimensional real vector space, and it gives some continuous data in which we can deform our setup. But let's fix one of these affine lifts, E. So staying away from the branch set for a moment, a section of E, of course, is represented in a local trivialization just by a map to our indefinite space, Rn M. And we'll say that a section is maximal if these local maps are embeddings with images maximal submanifolds. So we have a kind of a version of this maximal submanifold equation for sections of our bundle, which allows non-trivial twisting as we go around loops in our manifold. So what is a bit more tricky is to describe the kind of behavior we want to impose around sigma. But to make this a bit simpler, we'll do this in the case when M is 1, codimension 1 case. So we write, we're going to sort of describe a model. So let's fix our model affine space as a product of Rn with R. So you take a model reflection acting as -1 on the R factor. So suppose we have a codimension 2 submanifold S of Rn, and we're going to choose a diffeomorphism from S, well, from Rn to the product of C by Rn minus 2, and we want to choose a diffeomorphism of that from this Rn, which takes which way around again, which takes 0 times Rn minus 2 in here to our submanifold S. And then also we want to require that this behaves in a simple way with respect to the metrics on the normal bundle. So we have over this model situation, the complement of S in Rn, we have a flat bundle with fiber this Rn1, say V0, with holonomy this reflection. And we'll say that a section is branched in this model case if it's given essentially by a graph. So the component in the Rn variable is just the identity. And in the other variable, we get a section of this bundle V0, which can be written as, if we compose with our diffeomorphism phi to bring us back to the model case, this is given by this leading term that we saw before, the real part of some multiple of z to the 3 over 2, plus a lower order term. So this is a bit, we haven't been completely precise in various ways. One is really we should be talking everything local here. We should be talking about small open sets and submanifolds in those open sets. Also, when we've written this formula down, we've identified the flat bundles over the complement of S with the flat bundle over the complement of the sort of 0 times Rn minus 2. But clearly there's a that's not really a problem. So let's, I've never done this before. Let's see if this is going to work. What are we going to do? Okay, so do you now see my, I'm hoping you'll see, right. Okay, so this is, are you seeing my little?
Yes, we do.
Good, that's great. Because I haven't done this before, so so we have let's see. Let's start again. We have already 3 things going on here. So this is our manifold M containing sigma. This is our Rn minus 2, in which we have a submanifold S. And this is our sort of model product situation, C times Rn minus 2. So over here, we're writing down our function b of t times z to the 3 over 2 in terms of our standard coordinate z. We have a diffeomorphism taking this thing over here to some neighborhood here. And then, but we can also consider a diffeomorphism in our manifold, which taking this situation to this situation here. So for our branched section, we want something on our, which around sigma, we can take an open set in which it agrees with this model in the way that we've described. So now I go back to view full screen. Right, so I said this is not, I'm being slightly imprecise here about exactly the class of functions f that we want to consider. The main point is that the leading term should look like this model with a non-vanishing term b. But later, we'll, when we talk about function spaces and so on, we'll say precisely what kind of f we want to consider. But any sensible choice of definition of what f's you want to consider, one would expect to lead to the same class of objects. Okay, so actually, so I jumped the gun a bit. So going back to our global situation with M and sigma and E, we get a notion of a branched maximal section locally equivalent to what we said before. This is a bit confusing, I find. We didn't fix a metric on M, and so the problem on M is really diffeomorphism invariant. If we have at least a small diffeomorphism of M, then it takes a maximal section branched along sigma to one branched along the image of sigma under this diffeomorphism. Because the diffeomorphism is small, you can move the flat bundles around in an obvious canonical way. So the only intrinsic sort of diffeomorphism invariant continuous data in this triple is the data defining our flat bundle. In particular, this cohomology class chi, which varies the affine lift of our flat vector bundle. So what we're saying is that sigma really has no intrinsic geometric meaning inside M. So the main new result then that we talk about is that we have a similar deformation theorem in this setting. Supposing we have one of a branch maximal section with this condition that B is nowhere 0. Well, actually, I made that part of the definition, so you got that. Then if we deform continuous data, we deform this flat bundle E primed, then we can deform our branched maximal section in essentially a unique way up to diffeomorphisms. Okay. Okay, so that's the main result we want to discuss in these lectures. But maybe I'll just wait. Are there any questions anyone wants to ask? Maybe is everything reasonably clear? As we'll see in a few minutes, in the situations we'll be interested in, the flat bundle V, the vector bundle, will essentially be fixed because our orthogonal transformations will preserve some fixed lattice in our vector space. So the main application is to deforming this cohomology class chi. But it is possibly still interesting to be able to deform the flat vector bundle as well. Okay, so that's finished. That's finished our first section. We've explained the results that we want to talk about. So in this section 2, we're going to try to explain why, or to begin to explain why these could be interesting and what they have to do with other things, particularly in these lectures. We've already mentioned some of that in our discussion of quadratic differentials and so on. So the main interest is in the case when the dimension is 2 or 3, and then these ideas are related to considering Calabi-Yau threefolds and G2 manifolds, respectively, fibered over our base, over M as the base, with hyperkähler 4 manifolds as fibers. So we have some kind of picture like this. The dimension of Z is either 6 or 7. The dimension of M is either 2 or 3. Okay, again, I forgot to say this section is going to be quite vague. Quite vague. Because obviously it's no time to explain in detail really what I'm talking about. That should be the topics of other talks. Also, I may leave out things that work that I ought to mention, and I may make mistakes in the things I'm going to talk about slightly. So in particular, we're interested in this sort of situation, describing these manifolds of special holonomy, in a fibered situation, in particular to adiabatic limits when the fibers are very small. And so roughly, we expect to approximate the geometry in these higher dimensions by some limiting adiabatic geometry on M. And that's what we're talking about. So the deformation statements are counterparts of Torelli type theorems on our total space Z. For example, this cohomology class chi that we've talked about, say in the G2 case, for example, is essentially giving corresponds to the three-dimensional cohomology class of the 3 form over Z. So it's the counterpart of the fact that if we have one G2 structure, we can parameterize the deformations locally by the cohomology class of the 3 form in three-dimensional cohomology. So the harmonic 1 form setup, that arises when the generic fiber is a non-compact hyperkähler manifold. So in fact, the simplest case, the Iguchi-Hansen manifold from the point of view of a Riemannian geometer, or called the type A1 Milnor fiber, we could think of it if thought of as a complex manifold. And then this was discussed in Ivan Smith's talk. The fibers over the branch points correspond to points where these acquire ordinary double point singularities. So this is well developed in this Riemann surface situation. The base is a Riemann surface. Everything's expressed in terms of quadratic differentials. And there are at least some extensions of the discussion to other ALE fibers, as Ivan mentioned. In the case when our base is three-dimensional, then there are very much related constructions of Joyce and Carigianis, starting with a nowhere vanishing harmonic one form on the three manifold, and producing at least an approximate G2 structure on a seven manifold fibered over this three manifold with the Gucci-Hansen fibers. They did this as a component in their smoothing theory for compact G2 manifolds in order to find something to glue in to resolve the appropriate kind of singularity. There's also work of Rodrigo Barbosa, which I believe he gave a talk on this in the October meeting of collaboration, which develops this kind of picture in the three-dimensional situation for other ALE fibers, and also allowing non-empty sigma. So I should say this Joyce and Carigianis case would be when there's no branching, so the sigma is empty. We just have an ordinary one form on the three manifold. So the maximal submanifold setup, the more complicated one, this arises when the generic fiber is a K3 manifold. And then, of course, the fiber, we would take M is 19, so the fiber is the cohomology of the K3 surface. Well, that would be the case when N is 3. In the case when N is 2, you'd be looking at K3 manifolds with a fixed Kähler class. So the relevant fiber would be the part of the cohomology orthogonal to that fixed Kähler class. So the fact that we get these reflections coming in is the usual Picard-Lifshitz formula for the behavior, the monodromy around double points. So when N is 2, then this is, in a sense, probably reproduces standard theory and perhaps in a slightly different point of view. From the starting sort of thinking about differentiametrically, for a two-dimensional minimal or maximal submanifolds are special because there's a Weierstrass representation of them in terms of holomorphic data. So this leads to a holomorphic description of our branched maximal sections, which leads to a description in terms of a complex structure on the base and a holomorphic one form with values in this bundle. So remember that in our setup, M doesn't start off, M starts off with no structure essentially. So having this maximal positive section produces a complex structure on the base and also this holomorphic one forms. And this is the usual complex geometry point of view you would have on the Calabi-Yau threefold fibered over a Riemann surface with ordinary double point singular fibers. So we could also take M equals 3. That would be another case I could consider. That would be relevant to having where the situation where the fiber is a 4 torus, so R33 is the two-dimensional cohomology of the 4 torus. And this, in fact, was the context of the work of David Baraglia, he was the first person to introduce this maximal submanifold equation in G2 geometry, and in the context of fibrations with 4 torus fibers. But then we couldn't have ordinary double point singularities for some basic reasons. So if there was some other good class of singular fibers, one could maybe have a variant of this setup for corresponding to m equals 3. So another remark to make is we mentioned adiabatic geometry, and roughly speaking, the local geometry of our manifold Z is on the scale of the fiber approximating a product of a hypercalometric on X with flat space. But around the singular fibers, things become much more subtle, not far from being completely understood, but one should expect that the geometry around these double points of the singular fibers should be modeled on the metric discovered by Yang Li a few years ago. So there's a plausible model for how to describe the geometry of the total space in terms of these maximal submanifolds. But there should also be a theory with n equals 4, though it won't involve a different equation from the it involved, speaking of a variant of the maximal submanifold equation involving 2 forms rather than one forms. So which would be appropriate to spin 7 manifolds, but that is not worked out at all yet. So finally, to give more context, so remember the point of what Ivan was talking about with these quadratic differentials was then to develop a theory involving counting certain configurations of trajectories defined by the quadratic differentials on the Riemann surface, behaving in various ways with respect to the zeros and poles of his quadratic differential. But these were related to Lagrangian submanifolds, and I picked some relation to special Lagrangian submanifolds in the corresponding complex threefold, and hence to the Fukaya category of that threefold. So in the three-dimensional situation, there are similar, maybe I should call them ideas rather than theories, which count configurations of objects which locally are given by gradient flow lines and level sets of harmonic functions. And these are related to associative and co-associative submanifolds in the G2 setting. So when I say there are similar theories, I mean is that the geometry is very similar. Whether one can use these to extract sort of enumerative information is another question, which has been debated a lot in our collaboration meetings. But at least as far as the basic geometry relating calibrated submanifolds in Z to geometrical objects in the base, one gets very similar pictures in the three-dimensional case as the two-dimensional case. So in the case of ALE fibers, there's work of Pantov and Winault in this vein. In the K3 case, I have worked with Chris Gaduta, that again I talked about in previous collaboration meetings. You'll see the same kind of pictures of 3 gradient lines coming together at a point, and so forth, that one saw in Ivan Smith's lecture. Okay, so I think that's a good place to stop. A few minutes roughly on time. That's the end of our second section, in which I've tried to explain, well, first explanation of why these ideas might be interesting, and in particular related to special holonomy and possible enumerative problems. Tomorrow we'll go on, you've got norms and inequalities and things to talk about some of initially we'll talk about the analysis involved in proving these results, and then we'll have some more general sort of waffle about the context and related questions and so forth. So I think I'll finish. That's a good point to stop. Thank you.
Yeah, thanks a lot for this nice talk. And I guess we have plenty of time for questions.
Yeah, I have some kind of short question which might be related, maybe not. In this Greg Moore's talk, he mentioned some two-dimensional defects. So like in 3-Calabi-Yau, you have a complex surface and you count special Lagrangians with boundaries on this surface. So I don't know how to define the virtual class for this counting problem rigorously, but can I look for a 2-to-1 covering ramified over this surface and just reduce to the case of closed special Lagrangians?
So this would be a complex surface in the complex Calabi-Yau.
Yeah, I mean, I think I missed, unfortunately, the talk of Ivan Smith, but probably it's a story when you have a spectral curve, which is a complex curve in the cotangent bundle to some initial curve, whatever it is, and you look for the conic bundle, which is 3-dimensional Calabi-Yau, which is projected to this cotangent bundle and which is ramified of the spectral curve. So outside it's a conic bundle. And so you fix a point on the original curve for which spectral is a ramified cover. And you look for a surface which belongs to this conic bundle, which is non-compact 3-Calabi-Yau. Yeah. So this quadratic differential story, they correspond then to special Lagrangians, but with boundaries on this surface, which I believe Greg called defects in physics language. So then I would like to count these, fixing like discrete parameters, whatever. So then it's count special Lagrangians with boundary. And there is a kind of similar question for in G2 setting. So, but just is it possible to get rid of the boundary and count just closed special Lagrangians going to the 2-to-1 cover?
Yeah, I don't see. I mean, that sounds very interesting. I don't see anything very helpful to say. I'd have to think more. The case of special Lagrangians with boundary in a complex submanifold that I can see is when you take you take your complex submanifold to be one of these K3 fibers, and then you'd be looking at these essentially gradient paths or curves in the base, which happens to go through that particular point.
Yeah, correct.
And, so that, but I don't see this. The case you're describing, I don't really see anything helpful to say. but I certainly like to think about it more. It sounds interesting.
Yeah, okay, thank you.
So, seems there are no further immediate questions, but there is still time for discussion until 8 o'clock London time. So thanks again.
Thanks.